This live SLU show is brought to you by the support of SLU members and the following sponsors. Visit SLU.com to become a member today.
Hello and welcome to SLU.com. My name is Will Gator, and tonight we're discussing extrasolar planets, alien worlds, planets orbiting other distant stars. And the reason we're talking about that is because just a few days ago, scientists using NASA's Kepler Space Telescope announced that they had discovered a planet orbiting a distant star some 1,400 light years away that they called a bigger, older cousin to the Earth. It's 60% larger than the Earth, and it has an orbit that takes it around its sun in 385 days. So what does this all mean, and are we any closer to finding a true twin of our own little oasis in the solar system? Well, that is what we're going to be discussing tonight here on SLU.com. And we've got some fantastic guests. Don Jenkins, who was the lead author and in charge of the science team that basically discovered this planet and used the Kepler Space Telescope to sift through the Kepler data and uncover this intriguing world. And we'll be speaking to him later. Shortly, I'm also going to be speaking to Dr. Seth Shostak from the SETI Institute about what he makes of this planet, and maybe is this a closer step towards finding a habitable world out there in the Milky Way. But before we go into this, I want to draw your attention to what's on the screen right now. This is the location of the star in the constellation of Cygnus that this planet is orbiting. And in fact, the image you're seeing live on your screen right now is coming from one of SLU's telescopes located in the Canary Islands on Mount Teide. Up there on the top of the mountain, we have beautiful dark skies, clear skies at the moment. And these live images are coming down, showing you there is the star. So there is the star Kepler 452, right in the center of that little reticule there. And that is the star around which this intriguing new planet is orbiting. So as we go through the show, this image will show you these live images coming down from SLU's telescopes in the Canary Islands. But it's a lovely thing to keep that in mind. That is the star that we're talking about tonight and the planet going around it. But here's the live view that really shows it in context. And this is the region of sky that the Kepler Space Telescope has been studying. You can see, if you're a stargazer, you might recognize some of the constellations in this live all-sky image from the Canary Islands. That bright star to the right of the little reticule, that's the bright star Vega in Lyra. And the one just to the left, well, that's Deneb in Cygnus. And this field of view is a field of view where the Kepler Space Telescope stared at for quite a long period of time, studying thousands of stars. And what it was looking for is a tiny, tiny little dip in the light from some of those stars. And that dip in light would indicate to the astronomers that a planet had passed in front of its parent star, causing the starlight to momentarily reduce. And you see this little dip in light. And so this is how the Kepler Space Telescope has discovered numerous, hundreds of these extrasolar planets orbiting stars in this little patch of sky. And it is how, in fact, Kepler 452b as it's known, was discovered, going around a star that is in some ways quite similar to our own sun. So it's a fascinating system and one we're going to be talking about a lot more. But before we go on to talk about hows and how this actually happened in detail, I want to bring in our first guest. We're very lucky to have now on the line Dr. Seth Shostak from the SETI Institute. And Dr. Shostak, I wonder if we can bring him in live now. One of Dr. Shostak, thank you for joining us here on SLU.
It's a pleasure to be here, Will.
I think that in terms of the sort of hunt for extrasolar planets and discovering, other worlds that may potentially be like ones in our solar system, how exciting do you think this is? I mean, I'm pretty excited, but what's it like from your professional opinion?
Well, of course it's exciting. I mean, last year we had a comparable amount of excitement when the planet Kepler 186f was announced. Now, this was the best, if you will, candidate for being a cousin of our own world that had been found so far. And this one's a little bit better because it's around a star that really is very similar to our own sun. As you've already mentioned, this planet, Kepler 452b, goes around that star in 385 days. That's only 20 days. That's 3 weeks longer than here for Earthlings. That means you'd have slightly fewer birthdays. You would age a little bit less quickly, perhaps, or maybe you just die younger. And the other thing is that it's a little bit bigger than Earth. It's 1.6 times the diameter of Earth. I think John Jenkins can tell you all these details. But that's bigger. Yes, if you took a jet aircraft around the world, it takes maybe 24 hours to do that on Earth. It would take maybe 35 hours on Kepler 452b. But otherwise, at least in terms of these gross properties, it looks somewhat similar. There's also a better than even chance that it might be a rocky world. That's determined on the basis of statistical properties. It's exciting. The reason it's exciting is not so much that this world is where ET is hanging out. We don't know that. We've already started looking at it with the Allen Telescope Array. But what's interesting is that it suggests that there are a lot of such worlds out there.
So this is actually one of the things I think is quite interesting about this particular discovery. You mentioned Kepler 186f and how it sort of fits into all the other planets that we know about, because actually there are not many of these worlds that seem to be orbiting in the habitable zone of their parent stars that are rocky. We found actually most of them seem to be quite strange, don't they?
Well, I don't think we know too much about them. I mean, even in this case, we're not 100% sure that it's a rocky world. It might not be. All we know is the size, and we know the orbital period. We have not measured, for example, the wobble of its host star, Kepler 452. That would give you the mass. Kepler gives you the size, so you divide one by the other, and it gives you the average density, and that would tell you whether it's rocky or not. So the Kepler scientists have had to infer that it's probably rocky on the basis of other aspects of their measurement. So we can't be sure. But, if you go to the Habitable Planet catalog kept up by the University of Puerto Rico, and you look at what they consider habitable worlds, they're on the order of 36 of them. Now, I think that it's important to keep some perspective here. That's good. But what you really want to know is what fraction of stars have worlds that could be habitable. And we still don't know that terribly well, but we have a pretty good idea that number is not 1 in a million, 1 in 1,000, even 1 in 100, maybe not even 1 in 10. It looks like it's more like maybe 1 in 5, maybe 1 in 4, 1 in 3. That means there are tens of billions of such habitable worlds in the galaxy. The other thing to keep in mind is that, you could have, if you were a Klingon SETI experimenter, on some other world, and you were looking at the Earth with your big radio antennas, you could have looked at the Earth for 4.5 billion years without picking up anything. So, one should moderate one's expectations. We have looked at 452b with the Allen Telescope Array over 2 billion channels so far. We'll look over about 8, 9, or 10 billion channels, but so far, nothing. But, no reason to get discouraged. As I say, you could have looked at Earth for a long time. The bacteria, the trilobites, the dinosaurs, they were here, but they weren't building radio transmitters.
One of the things you mentioned is the habitable zone. Could you explain for our viewers what that actually is? Because it doesn't necessarily mean that it's a habitable planet, does it?
Well, it doesn't. The habitable zone is just that region, that donut, as you see in the graphic here, that region around a star where if a planet is there, the temperatures, based on the amount of sunlight hitting it and nothing else, the temperatures there will be above freezing. So it won't have solid ice if there's any water there, and not below boiling. So if there was any water there, it didn't just all boil away. In other words, you could have liquid oceans and so forth, and atmosphere, presumably, on a planet that was in that habitable zone. Now, a couple of things. I mean, just because a planet's in the habitable zone doesn't mean it's inhabited, right? I'm trying to think. You go to Egypt and you see all this limestone sitting around, but that doesn't mean they're going to be pyramids too, just because pyramids are made out of limestone. So the fact that a planet's in the habitable zone, that's a good sign, but it's no guarantee. And the other thing that astrobiologists love to point out is that there are plenty of places in our own solar system where there might be life that are not in the habitable zone. For example, some of the moons of Jupiter or Saturn, they could have microbial life under the surface there. And those worlds are far beyond the habitable zone as it's traditionally defined.
We've got these views actually that we've taken with SLU's telescopes of Jupiter and Saturn. It's exactly what you say. Do you think we should broaden out our sort of definition of where we're looking for these, quote, habitable planets? I mean, we've got these pictures that we took with the SLU's telescopes in the Canary Islands very recently, and you mentioned some of these icy moons that are going around Jupiter, Saturn, things like Enceladus and Europa. Should we be looking for those equivalents in some of these alien systems?
Well, yes, you should be. It's not easy to do that, however. Look, there are only three ways you can find life in space, as far as I can tell. One is you just go there and look. Okay, you can do that for Mars and some of these moons in the solar system. That's where the big money is. That's where NASA is spending a lot of money, the European Space Agency and so forth. Okay, that's one way to do it. The second way to do it is to build a big telescope and analyze the light being bounced off a planet, such as 452b, if you could see that, which would be very difficult, but if you could see that, and you would just spectrally analyze that light, pass it through a prism and say, well, I don't know, Bob, but it has oxygen in the atmosphere. So, maybe there's some, cabbage or something dependent on photosynthesis on that planet. That's the second way to find it. And the third way is to look for signals, artifacts, some sort of indicator of intelligence. And that's what SETI does. Now, in the case of 452b, it's so far away, 1,400 light years away, it's very difficult to, obviously, we can't go there. You could go there, but it would take, like 50 million years in our fastest rockets. That's a long time to sit in the middle seat. So you're not going to do that. You can't get a spectrum of that world because, it's so far away, it's very hard to do that. And the only thing you can do is, look for radio signals. So we're doing that. But again, it isn't so much 452b, it's the significance that 452b shows that there are worlds around stars like the sun that could have the conditions that could cook up something interesting.
You mentioned that you've already been looking at this planet with the Allen Telescope Array. What does that actually involve?
Well, the Allen Telescope Array is an array of telescopes or antennas in the radio astronomy world. Each of those antennas is about 6 meters, they say 20 feet in diameter. And this array extends over about a kilometer of real estate, which is mostly useful for feeding cows, up about 300 miles, 500, 600 kilometers north of San Francisco in the Cascade Mountains. Now, it's located in the Cascade Mountains not because the scenery is beautiful or because the cuisine is exceptional. It's there because those mountains kind of block the interference that comes from the San Francisco Bay Area, all these transmitters, millions of people using electronics and so forth. So the mountains kind of shield the antennas from that. That's really why it's located up there. Anyhow, these 42 antennas, and that's the number, 42 of them there, are all trained in the same direction, in this case, in the direction of Kepler 452b. And then we slowly step up the radio dial looking for a signal that would say, there's somebody there that's built a transmitter.
And it's 6 billion years old, this system. So does that make you more confident? If you potentially should be looking at older systems like this one?
Well, I have to say that, every year I become slightly more sympathetic to older systems. But this may be just one case where being older is better, actually, because, look how long it took for intelligence to spring up on Earth. You've had life on Earth for at least 3.5 billion years, probably 4 billion years. For the first couple of billion years of that, up until fairly recently, all that life required a microscope to see. It was all, just microbes. And microbes are great, but they don't write great literature and they don't build radio transmitters, okay? So it took 4 billion years of life to produce Homo sapiens, and then Homo sapiens just sort of fiddled around for most of 200,000 years, and then in the last 100 years was able to invent a radio transmitter. So if you have a really old star system, and in this case it's what, 1.5 billion years older than our own solar system, then it's had all that extra time for this kind of complex, sophisticated life to get going, and maybe to develop the science and the technology that would allow it to get in touch with signals that we might pick up.
We've talked a little bit about those sort of parameters that we actually don't know about Kepler 452b, but what to you would we have to know about a planet, maybe not this one, but maybe just another planet, before you would confidently say, yes, we're looking at a twin of the Earth? You know, what sort of things that we would have to tick off on our checklist to find this sort of Earth 2.0, as some people have been calling these planets?
Yeah, I'm not sure there's a very definitive answer to that. I mean, if I ask you, you have a dog, what characteristics would another dog have to have before you'd say that's a twin of your dog? Okay, so I
Yeah.
mean, but obviously, if it had a mix of oceans and continents, if you knew that, and it might not be impossible to know that, if it had an atmosphere, a thick atmosphere, comparable in density to the atmosphere of the Earth, and that alone, those things together with the temperature range that we've already discussed and the size and the composition, rocky, then I'd say, okay, that's a twin of Earth. And of course, finding one, and not, for example, finding oxygen in its atmosphere would be interesting, because you would expect that such a world with the land masses and the water and all that stuff, you would expect that it should cook up some biology, and eventually maybe that biology would figure out that oxygen is a much better way to make a living than methane or whatever it was doing in the first 2 billion years. So, you could do some real experiments there that would mean something. In general, when you look at a planetary system and you don't find any indications of life, it really doesn't tell you too much.
Well, Dr. Shostak, thank you so much for speaking to us here live on slew.com. For now, though, we're going to take a short commercial break, but actually we're doing lots of things here on Slew. Coming up in the next couple of weeks, we've got some fantastic meteor shows, actually. We've got the Delta Aquarids coming up very shortly, in just a few days, in fact, and we're going to have a live show there on the 28th of July, 9 p.m. Eastern Time. And then, of course, on August the 12th, it's the Perseid meteor shower, one of the best meteor showers of the year. And so that's going to be going out, and we're going to have our cameras looking to the skies, and also some special equipment to see if we can hear the meteors, see if we can detect them through radio methods. So there's lots coming up on Slew, and in fact, we're also going to be teaming up. There's a little bit of a teaser for you. We're going to be teaming up with the European Space Agency and our observatories in the Canary Islands to get a live view of the comet that Rosetta, the European Space Agency mission, the comet that Rosetta is currently visiting. That's Churyumov-Gerasimenko. And so we're going to be bringing some live views in the coming weeks of that comet. So that's a very exciting show to look out for. But for now, we're going to take a short 30-second break. And when we come back, I'll be speaking to the lead author of the Kepler 452b study, and that's Dr. John Jenkins from NASA. So join us in 30 seconds, and I'll see you again then. Well, welcome back to our live coverage here of the Kepler 452b discovery, a discovery of a world that NASA calls an older, bigger cousin to the Earth. And it's an interesting world, certainly in our search for planets that are truly like the Earth. And we're very lucky to be joined now by the lead author of the paper of this particular study from NASA's Kepler team, the lead author, Dr. John Jenkins. Dr. Jenkins, thank you so much for joining us here on Slew.
Well, thank you very much, Will. I'm happy to be here.
What was it like? One of the things I always love asking scientists is what it was like that moment you realized you'd found something new.
Well, absolutely terrifying, actually. It's very thrilling. lots of emotions. We've been working on this spacecraft and this mission for, in my own case, for 20 years. We built this spacecraft and this mission specifically to find this kind of planet in this kind of orbit about this kind of star. But there are a lot of things that can go wrong when you find a planet signature like this. There can be background eclipsing binaries that are fooling you, that are slightly offset on the sky, but are causing the transit-like signature consistent with a planet. There are instrumental glitches that can fool your software. And then you can look with your ground-based observatory and find that there's a very dim star very close to your target star that you can't even see in the Kepler data. That could be the cause of the blips that you're seeing. So it's absolutely thrilling, but it's also terrifying. So you start working on the data, you go over the data with a fine-tooth comb to try to make sure there's nothing wrong with any of the measurements, with the pixel data, with the flux measurements, brightness measurements, and then you hand it off, of course, to your buddies at the telescopes to refine the characteristics of the star. So one of the interesting things that often happens with Kepler targets is that we don't understand the stars as well as we would like to. So when you find something interesting, you go to a medium resolution spectrograph and you try to get updates for the size of the star, because we only know the size of the planet as well as we know the size of the star. In this case, our initial estimate for the size of the star was that it was about 80% the size of our sun. And that turned out to be wrong. So our initial estimate for the size of the planet was 1.1, only 10% larger than Earth. Now, indeed, that would have been very exciting indeed. But it turned out that the star was 10% bigger than the sun. And that means that instead of being 1.1 Earth radii, this planet is 1.6 radii. So it's very important to dot all your I's and cross all your T's, and all of that takes a lot of time.
You can get a sense of that almost sort of needle in the haystack sort of discovery process. We've got these live images that we're showing of the actual star that this planet is going around. And this field of view, we said earlier, we briefly mentioned that it's in Cygnus. Could you describe a little bit how Kepler actually went about this process of looking at this star, and I guess many others like it, to discover these planets?
Yeah, so how Kepler works is that we're looking at a field of view at 160,000 stars simultaneously all the time. And the idea is that you never know when the stars are going to wink at you, right? So you never know when a planet's going to cross the face of its star from your point of view. So the idea is to look at them as continuously and contiguously as possible, watching for the faint drops in brightness corresponding to those transit events when a planet crosses the face of its star from our point of view. So in 2009, we launched a spacecraft with a telescope, basically with a 1.4 meter diameter mirror and a 0.95 meter aperture, a Schmidt-type design. And at the heart of this telescope is a focal plane array with 42 charge-coupled devices, each of which is similar to the camera chip that's in your cell phone, but a little bit bigger. These are 1 by 2 inches for each of these chips. And the focal plane itself is about a foot across. So this is actually the largest physical focal plane that NASA has ever launched. It's not the largest camera pixel-wise. We have 96 million pixels. So while we were operating in Kepler, we would stare in Cygnus at the Kepler field of view, taking images every 6 seconds and co-adding those images to build up a half-hour image. Then we would cut out the pieces, the postage stamps, for each star that we were interested in, and we would package those on board and store them up for about a month. We would send those down once a month, and then that's where the data processing team at Ames would get to work. We would do all the pixel level calibrations that are common to most ground-based CCD observations. There were some specific to Kepler. For example, we don't have a shutter on Kepler, so there's an image smear during the readout that you have to estimate, measure, and remove, for example. Once you've measured the brightness as a function of time, then you have to identify and remove systematic effects, because the temperature state of the telescope itself is changing slowly over time. That means the focus is changing, the positions of the stars are changing, and all of those changes cause changes in the brightness measurements. So you have to fix those. At that point, you're ready to start searching for these little golden needles in the haystack. And that's quite a computationally intensive challenge. And in fact, routinely now we run all of our processing on the supercomputer, the NASA Pleiades supercomputer at Ames, because otherwise it would take us years to reprocess all the data on the original computer clusters we had that had 700 computers in them, right? So once you find something that looks like a planet signature, that looks like a periodic sequence of dips in brightness that might be as small as 100 parts per million, and in the case of this planet, the dips in brightness were 200 parts per million, lasting 10.5 hours, repeating once every 385 days. So there are only 4 of them in the entire data set. Well, at that point, then you conduct a suite of diagnostic tests to tell whether or not it's likely to be a planet or more likely to be a background eclipsing binary. So as I said before, sometimes an eclipsing binary will be offset on the sky slightly, maybe a pixel away, 2 pixels away. In those instances, if you measure the position of the image of the star over time and correlate that against the change in the brightness, you'll see a strong correlation. That's an indication that you have a crowded scene, and you need to work out whether it's a change in position due to the fact there's a background eclipsing binary, or whether it's due to the fact that you have a stable background star and it's a planet. Now, fortunately for 452b, the scene was relatively clean. We went to the Keck telescope and did adaptive optics and looked for stars in the neighborhood too close to the star for us to see either through our catalogs or through the Kepler data, and that was absolutely clean. We went to the Keck also to get our high-res spectrum so that we could get our final stellar parameters. So that resulted in a radius for the star of 10% bigger, mass that's about 4% bigger than the sun. That means the star is 20% bigger, 20% brighter. Fortunately, the planet orbits 5% larger than that of Earth. And so overall, the brightness of the star from the planet's point of view is only 10% more than the Earth relative to the sun. So that means that this planet is receiving about 10% more energy from its star, and that's what places it so close to our own Earth with respect to the habitable zone.
Right. And so we can see this.
Now that
we can see.
Go ahead.
So I was going to say, we've got this lovely graphic showing a sort of almost a migration through the habitable zone, I guess, as the planet ages, because as I mentioned with Dr. Shostak earlier on, we were talking about how it was a much older system, and so presumably it's slightly more advanced than our own.
Yes, indeed. With respect to the evolution of the star, we expect that when this star was very young, it was about the same size as the sun was when the sun was young, and about 8% of its current size at the start of this animation. And that over time, stars basically burn hotter as they accumulate a helium core, and they get brighter. And so what happens is that a planet then, as its star ages, receives more and more radiation over time, especially for G stars and stars that are more massive than M stars. So we see on this animation, though, that the sun and the Earth are quite the same, right? The Earth is following in the footsteps of its bigger, older cousin, so to speak. And 1.5 billion years from now, the radiation we receive on Earth from our sun will be 10% greater than we receive today. So that's very interesting from a habitability perspective from the Earth's point of view, because at that point in time, the Earth will be on the verge, according to some models, to start experiencing a runaway greenhouse effect. For this planet, because it's 1.6 Earth radii, 60% bigger, we can only predict a mass for it, but based on observations of small exoplanets for which we can make direct mass measurements, and we have the sizes, we can predict that the mass of this planet would be about 5 Earth masses. With that much bulk, this planet is today, at its current energy level, protected against the runaway greenhouse for a little bit longer, so for perhaps another 500 million years or so.
One thing I want to share with our viewers at the moment is something we did. You mentioned earlier looking for those dips in light, and we actually did a live show here on SLU looking at just such one of these transits. So we were looking at the exoplanet TRES 2b, and here is the light curve that we were able to capture live of that particular transit. So this is something that I guess in terms of discovering extrasolar planets, we're doing all the time. But one thing I wanted to ask you about this particular planet is how confident are we that it's a rocky planet and not, say, like a Neptune gas giant? Because I guess this is one of the key questions as to exactly how Earth-like, to use a phrase, this planet actually is, right?
Yes, absolutely. We would love to be able to do a mass measurement and do a direct mass measurement so that we can measure the density. And that would give us a really big clue as to whether or not this is rocky or whether it's a water world or whether it's a gassy world. But unfortunately, the star is 13.4 magnitudes, and it's too dim for us to measure the reflex velocity with spectroscopy, with Doppler radial velocities. You expect a reflex velocity of about 45 centimeters per second, and the star is too dim for that. So all we have to go on is to look at the statistics of the distribution of planet masses versus their size for small exoplanets orbiting stars that are bright enough so that we actually can measure their mass in addition to their size. And those models predict that at 1.6 Earth radii, this planet has a 50% chance of being rocky. So now it depends on what the stellar parameters actually are. And there are some instrumental and other effects that give us some uncertainty in those. And so we chose in the paper to use the most conservative model, which gave us 1.6. Another very popular and highly respected model gave us 1.5. If indeed it turns out that this planet is only 50% bigger than the Earth, then the probability that it is rocky is more like 62% or so. So that's why we say that the odds slightly favor this planet being rocky. Now, that doesn't mean that it's Earth-like in the sense of having continents and oceans and giraffes and zebra and all that good stuff. But it does mean that you have the possibility, if it is rocky, of having water pool on the surface in some kind of ocean format.
Actually leads really nicely into this. We have a question from someone on Twitter who's watching us live, and they ask, is there anything we can infer about the atmosphere using telescopes, I guess, that we have today?
Well, if this planet were a lot closer to us, then the answer would be yes. We have technology that NASA is developing to allow us, and in fact, people already from the ground, and with the Spitzer telescope, for example, are studying the atmospheres of exoplanets. But these are exoplanets typically that are much larger than this planet, and they're orbiting stars that are much brighter. So you can get more photons and spread that light out in a spectrum and do a more detailed analysis of what elements and what chemicals might be in the atmospheres of these planets. So in some sense, the most important aspect of this discovery is the fact that it reminds us the most of our own planet-sun, Earth-Sun system. It's the size of the orbit, the size and temperature of the star, and the fact this is a small planet that has some good chance of being rocky, though we don't know. That means that we have a really good opportunity in the future to find a similar sized planet in a similar sized orbit about a similar star far closer to us, so that we could hope to follow up 20 years, 30 years down the road. If you look at NASA's roadmap, the hope is that in the next 10 to 15 years, we'll be able to find super Earths like this in much closer orbits. So hot super Earths could be found and have their atmospheres characterized with the James Webb Space Telescope. But we need additional instrumentation and larger telescopes to be able to characterize the atmosphere of a true Earth analog orbiting a sun-like star. And that's something that we all want to do. And we're building the technology today, but it requires that we may need to launch telescopes as big as, say, 10 to 12 meters. And today, that's a really heavy load to lift. It's not possible today.
Well, I guess there's in many ways there's lots to look forward to in this search for Earth-like planets that are truly with oceans and all these things, and it seems like there's a lot more we have to learn. But Dr. Jenkins, thank you so much for coming on to speak to us about you and your team's discovery. And we're actually going to be doing a lot more here on SLU about extrasolar planets. We're going to be doing more of those live shows where we show these transits, these passages of planets in front of their parent stars. So lots more extrasolar science and live shows coming up here on SLU. For the next couple of weeks, though, we've actually got some more shows coming up, more towards the sort of stargazing side of things. So we're going to have some live shows looking at some of the meteor showers that are coming up. So we've got the Delta Aquariids that are going to be coming up in just a few days on the 28th of July. And then, of course, it's the Perseids on the 12th of August, that fantastic meteor shower, beautiful meteor shower to go outside in those summer months and look up. And of course, as I mentioned earlier, if you heard me speaking about, we're going to be teaming up with the European Space Agency to look at Rosetta's comet, that comet Churyumov-Gerasimenko that's sort of entranced us all, those incredible sort of faint sort of wisps coming out from the comet that now we can actually see the tail growing in our ground-based telescope. So we're going to be bringing you live images of that comet. But from me here on SLU.com, I leave you with this live image of Kepler 452. Thank you to our guest, Dr. John Jenkins, who came on to talk about his discovery of this extrasolar world, this planet orbiting a star 1,400 light years away. And also thanks to Dr. Seth Shostak for giving us his perspective on these incredible alien worlds. But as we leave you with this beautiful all-sky image here, showing that location in Cygnus, if you're going out tonight stargazing, or maybe next few nights, have a look up in that patch of sky between Deneb and Vega there, and just think about those worlds that we know are orbiting there. And I think if there's one thought I want to leave you with tonight, it's that one. So good night from here. Good night from me here on SLU.com, and we'll see you again next time. Good night. There, and that is the star around which this intriguing new planet is orbiting. So as we go through this show, this image will show you these live images coming down from SLU's telescopes in the Canary Islands. But it's a lovely thing to keep that in mind. That is the star that we're talking about tonight, and the planet going around it. But here's the live view that really shows it in context, and this is the region of sky that the Kepler Space Telescope has been studying. You can see, if you're a stargazer, you might recognize some of the constellations in this live all-sky image from the Canary Islands. That bright star to the right of the little reticule, that's the bright star Vega in Lyra, and the one just to the left, well, that's Deneb in Cygnus. And this field of view is a field of view where the Kepler Space Telescope stared at for quite a long period of time, studying thousands of stars. And what it was looking for is a tiny little dip in the light from some of those stars. And that dip in light would indicate to the astronomers that a planet had passed in front of its parent star, causing the starlight to momentarily reduce. And you see this little dip in light. And so this is how the Kepler Space Telescope has discovered numerous, hundreds of these extrasolar planets orbiting stars in this little patch of sky. And it is how, in fact, Kepler 452b, as it's known, was discovered, going around a star that is in some ways quite similar to our own sun. So it's a fascinating system, and one we're going to be talking about a lot more. But before we go on to talk about hows and how this actually happened in detail, I want to bring in our first guest. We're very lucky to have now on the line Dr. Seth Shostak from the SETI Institute. And Dr. Shostak, I wonder if we can bring him in live now. Dr. Shostak, thank you for joining us here on SLU.
It's a pleasure to be here, Will.
I think that in terms of the sort of hunt for extrasolar planets and discovering, other worlds that may potentially be like ones in our solar system, How exciting do you think this is? I mean, I'm pretty excited, but what's it like from your professional opinion?
Well, of course it's exciting.
Hello and welcome to slew.com. My name is Will Gator, and tonight we're discussing extrasolar planets, alien worlds, planets orbiting other distant stars. And the reason we're talking about that is because just a few days ago, scientists using NASA's Kepler Space Telescope announced that they'd discovered a planet orbiting a distant star some 1,400 light years away that they called a bigger, older cousin to the Earth. It's 60% larger than the Earth, and it has an orbit that takes it around its sun in 385 days. So what does this all mean, and are we any closer to finding a true twin of our own little oasis in the solar system? Well, that is what we're going to be discussing tonight here on Slew.
This live Slew show is brought to you by the support of Slew members and the following sponsors. Visit slew.com to become a member today.
And we've got some fantastic guests. Don Jenkins, who was the lead author and in charge of the science team that basically discovered this planet and used the Kepler Space Telescope to sift through the Kepler data and uncover this intriguing world. And we'll be speaking to him later. Shortly, I'm also going to be speaking to Dr. Seth Shostak from the SETI Institute about what he makes of this planet and maybe is this a closer step towards finding a habitable world out there in the Milky Way. But before we go into this, I want to draw your attention to what's on the screen right now. This is the location of the star in the constellation of Cygnus that this planet is orbiting. And in fact, the image you're seeing live on your screen right now is coming from one of Slew's telescopes located in the Canary Islands on Mount Teide. Up there on the top of the mountain, we have beautiful dark skies, clear skies at the moment. And these live images are coming down, showing you there is the star. So there is the star Kepler 452, right in the center of that little reticule